To the second day. We had the contest yesterday, and teams did very, very well. There can be two explanations possible for this. One is, I'm a great teacher. One is the exam was too hard. So let's take, it was too easy. So let's make a check. Who here thinks I'm a great teacher? Who here thinks the exam was too easy? Okay. Now forgetting the first option, who here thinks the exam was too easy? Confess. Okay. I have a few people wanting it, saying it was too easy. I have directed Tanzir, okay, to add a few tougher problems to it, okay, for the next time. But we will see whether he's in a different time zone, a different, So we're all spread around the world, and we'll see whether or not this happens for this class. But anyway, there were 7 teams that got 11 problems, all 11. The winning team was Kanye East. Who's Kanye East? Do we have Kanye East here, or? Wait, stand up just so I see you guys. Okay, very good. Okay. You're Kanye East alone?
No, my teammate couldn't come.
So they don't think I'm such a great teacher. It's okay, very good. Anyway, very good, and for all of them. Because people did pretty well, I don't know how much it pays to go over some of the problems, but I guess the problems people had trouble with were E, J, and K, okay? I have a slide, but I'm afraid to touch the machine. Which is problem E? Does anyone remember? Can anyone look this up very quickly? Because I'm afraid to touch the machine. What? Harry Potter problem, okay? Does anyone remember what can anyone explain the Harry Potter problem and then tell me how you did it? So speak loud, and you can even come up here if you want. Okay.
So I believe problem E
Oh,
is
here.
the one that you have like a range of integers, and you have to count how many integers in that range had the property that every digit appeared an even number of times, right? Okay. So I remember the statements. So as usual with these kind of problems, you only need to care about one of the ends, because you can then subtract the answer for the other.
Sorry about that. Okay, we're going to get killed. One of us is going to get killed with this. Let's try this here. Actually, wait, do you have this? Is this possible? Try this.
So as usual with these kind of problems, you can just ignore one of the endpoints, because you can just compute how many numbers less than one number have this property, and then you can subtract it for the initial value, and you get the number of values in the range. Okay? So what you have to do for this problem, what we did is, so for example, you first represent the number in the base that you're given. Say it's 1, 0, 0, 1, whatever. So for a number to be less than this, it has to match a given prefix, right? And then it has to be less at some given point, and then it can be whatever at the rest, right? So for this, what you have to do is, so suppose it matches all this prefix, and then it's less here. So it's going to be 1, 0, 0, then a 0, and then something, right? And you want to count how many somethings there are. And that something has to be, so in this case we only have one digit, but imagine we had many digits. You have, in this case, 4 slots that you have to fill. And you have to paint these slots with B colors, where B is the base. And you have the restriction that, for example, in this case, you already have 1, 1. So the number of ones has to be odd for the total number to be even, and the number of zeros is also odd, so the number of zeros here has to be odd as well for it to be even, right? So you want to compute that problem separately using a DP. And once you compute that problem separately, you can use it to solve the complete problem. So what is a problem? You have n things you have to color. You have b colors to color it with. And you have a set of I colors, which is between 0 and b, that has to be odd. There has to be an odd number of elements colored with that color. Okay? Is everyone following? Okay. And this can be computed using dynamic programming. So, what we first did is count a slightly different problem, which is how many ways are there to color n things with b colors, such that there are I colors that appear an odd number of times. And this is different from the original problem, right? Because the original problem, we had a specific set of I colors that had to appear an odd number of times. This problem I'm saying here, there exists a set of I colors. Is everyone following? Yes? Any questions? Okay. And this has a dynamic programming solution, so you have DP of n b I is going to be equal to, well, first of all, it's going to be the DP of n minus 1. So you take n minus 1 things that are already colored. B stays the same because the number of colors doesn't change. And then you have, in the previous step, there were either I minus 1 colors that appear an odd number of times, or I plus 1 colors that appear an odd number of times, right? And when you added a color, that changed. So one possibility is I minus 1. And how many ways are there to do that? Well, you have to multiply by n minus I minus 1, because that's the number of colors that did not appear an odd number of times. And when you add those, you get a problem of this sort, right? And the other possibility is DP n minus 1, b and I plus 1. And in this case, you get I plus 1, I think, directly, because that's the number of colors that, when added, lower the number of odd number colors. Is everyone following? So this is the DP that accounts for n things and b colors. How many ways are there to color those such that I of the colors appear an odd number of times? If we want to compute, and this is not the DP we want, right? The DP we want is for a specific set of I colors. How many ways are there to do that? And to compute that, we have to compute, I know, DP prime is DP prime of NBI is going to be DP NBI divided by, so N choose, B choose I. Right? Because there are that many ways of choosing the set of colors. And it turns out if you replace this into the recursion, into this DP, all the divisions cancel out, and you just get a recursion like this where you don't have to divide at any point. You just have to replace that, and that works. So you can do a straightforward DP without having to work modulo anything. It just does it modulo 2 to the 64, which is enough to solve the problem. So that's how to compute the DP, and using that DP we can go back and compute the original problem. In the original problem, however, you had, like I told you, how to compute the number of, so it matches a prefix, then it's different at some point, and then you can do whatever afterwards. There's another case you have to consider, which is the case where it has less digits than the whole number. That's a special case because of the leading zeros. So you have to consider that specially. So you have to take any even number of digits that is less than the number of digits of the whole number, because for it to make sense, the number has to have an even number of digits, right? So in this case, you have 1, 2, 3, 4, 5, 6. 6 is an even number that is less than the number of digits. So the first digit has to be a non-zero. So you add a non-zero here, and then you compute using the same DP. How many ways are there to fill these in? And you do that for 4 digits as well. So the first one has to be non-zero, and you compute the rest using the DP, and so on. And that's all the possibilities. Any questions?
Very good, thank you. Yeah, you can clap for him, that's good. Okay, good. Actually, if we get our, assuming we get everything done that I want to do, next class will be about combinatorial objects, and they will be counting and generating recurrences. So if this is the skill of generating, I call this a recurrence relation, a recursive equation. And, you know, learning to formulate those is an important skill. I imagine many of you are pretty good at it, but we're going to talk about combinatorial objects and counting and what you can do if you can count. Next class, okay? Any other problem people really want a go-over for that they want, or should we move on with the material now? Yes?
Can you explain the problem K?
K was also one somebody did. Again, I'm afraid to touch this machine now. Does anyone remember what problem K is? Okay.
I can explain the statement.
Explain it, go ahead, here, come on up, get the mic.
I didn't solve it in the concept, but I know the idea.
Okay, good. Okay, can you hold the mic and
Yes.
write with
Yes.
your hands? Okay. that's
I think so.
impressive. Okay, good.
So problem K, let me know if I'm mistaken. I think it's you have an array of numbers and you want to split it in pieces, and the value of each piece is the amount of distinct elements in that piece. And given a fixed amount of pieces, you want to maximize the sum of all the values. Is that right? Okay, good.
You can erase if you want.
Yeah.
It's very nice handwriting. This I can do. You look like this much I'm good. Go.
All right, so we're going to have some sort of array, and we're going to think about solving the problem for some prefix at some index I. And we're going to solve it for some amount of pieces, k, right? So we're going to split it into k pieces. And the solution for this sub-problem, we're going to call, I don't know, say v at ik. And there's a pretty straightforward DP solution that's like too slow, but I think it's worth going over. The idea is just try cutting in a bunch of different places, right? So we're just gonna say, well, this is gonna be the max for some position j that we're gonna cut, where j is gonna be. Oh, mic's off. Uh-oh. There you go. So we're gonna cut at some index j less than I, and that's gonna be, well, whatever the amount of distinct elements between j and I is, plus, well, the solution for the rest with one fewer piece. So it's gonna be like v at j
Okay.
k minus 1. And of course this works. That's like the most simple, straightforward solution. But as we can see, the state space is going to be, well, this has n possible values, and this has something like k possible values. And here we have to look through something like in the order of n different things. So we end up with n squared times k complexity, and that's going to be too slow. And here the observation is that this is a bit hard to prove. But if we know the optimal cutting point for some IK pair, we know that if I decreases, let's say this is some I prime less than I, then the optimal cutting point cannot increase. So we're going to have some new cutting point, J prime, that's going to be less than or equal to J. And this allows us to do a nice trick that's called divide and conquer optimization. So I'm going to try to explain that kind of quickly. The idea is, for a fixed k, we're going to compute all the values of vik. Right? So we're going to start with k equals 1, which is very easy, because we just want to say, well, in a given prefix, what's going to be the amount of distinct elements, right? We can do that with a for loop and a set. It's going to be very easy. So we can easily compute vi1. It's going to be some nice array that's easy to construct. And then we're going to, given some vik, we're going to construct vik plus 1. The way we're going to do it is we're going to first compute the middle element. Okay? And the idea here is we're going to compute it just using this definition. We're literally just going to loop. Okay? We're going to loop and we're going to perform these queries as they come up. So we're going to have to look through this part of the array. Okay? Now the cool thing is, since we know that the optimal cut is going to be somewhere around here, when we compute dp for all of these values, we know that the optimal cut is not going to increase. So we only need to look in this region. Okay? And when we compute dp for all of these values, we know that the optimal cut is not going to decrease. So like we sort of flip around this inequality. So we know that it's going to be like around here. And in particular, when we compute this element and this element, as you can see, we end up looking at every entry once, right? And that's kind of convenient. So the first one took like O of n, but these two are also going to take O of n queries. And then we keep splitting, and we keep getting this nice result that on each level of splitting, we look at every entry once. Okay? And so as we split in half, and in half, and in half, we're going to have only log n levels of splitting. And we, on each level, look at every entry once, right? So there's n entries. We look at them log n times. So we will look at each entry n log n times. And we have to do this for every level, right? So we can compute this CP in kn log n time. But of course, I'm lying, because this is not taking into account that we have to do all these distinct queries, which are kind of difficult. So this is going to be multiplied by some sort of Q, like the cost of a query. And this is as far as I got during the contest, and then I asked someone. And they told me that what you can do is just keep, roughly, I didn't look at the code, didn't implement it, but just keep like a multiset. Probably like you can use some sort of array to do this efficiently. And when you, that's going to correspond to the last query that was done. And when a new query comes, what you do is you just add all the missing elements and remove all the elements that you don't need. And the claim is that this ends up being fast.
Okay.
But I don't know how to prove that.
Okay, fair enough. Okay, let's thank him for this. Okay, thanks. Okay, we can move on, or there can be another problem. If anyone really has a problem, they kill. What?
Problem G.
Problem G. Does anyone remember what problem G is and remember a solution? Okay. Okay, let's just see, to spread the wealth. Let's say you come over here. Here, use this.
Okay, so
Turn it on.
oh, it's okay. Hey, cool. So if I remember well, problem G was
Oh, this I do erase.
okay. Problem G was like that you had an array of numbers and they wanted you to compute if there was another number in the array that would make with an AND that number 0, right? Okay, perfect. Oh, here. Okay, so the basic idea is like a possible solution would be like the really dumb solution would be go through the array and do an AND operation on each element, right? And if you found one that made the number 0, record that as the answer and do it for every number, right? The problem is that it has like a complexity n squared, and we cannot like calculate that. So an idea you might have is like, if I look at if I have like a number 1, 0, 0, 1, 0, I know like which numbers this could make 0 by looking like at the spots where 0 are. If you put like a 1 and the rest of the positions are 0, right? If you put like the opposite number, then this would cancel out, like the ones would cancel out the zeros, right? And you would get zeros all the way down when you do the AND operation. So then the idea after that would be, how can I calculate this like opposite operation quickly and like do all the cases? Because like you could just do the opposite for each one, but that doesn't cover all the cases, because if you have like zeros in the same place, in places you can have zeros in the same places and this would still give you all zeros, right? So then the idea would be like, the idea we had was you just need to like do the opposite number and that would give you like a number you can take off ones from, right? But then this would take a lot of calculation because it was a 20-bit number, right? And for each bit that was in the opposite number that was a 1, you had to take out a 0. You had to like put it in 0 and check that you had a number that responds to that query. But you didn't have to answer like the number of numbers that could do this. You only had to answer the one number that could do it, right? So the thing is, you could do ADP, where you save like if you have calculated a result or you haven't calculated a result. So this means that instead of doing like every time taking out a 1 and taking out a 1 and doing all the combinations, that would take 2 to the 22, I think was time. You could just save the result, and if you have a result, you don't have to recalculate like that part of the EP. So in theory, you're only doing 2 to the 22 once, right? For each number in the array that was like 1 to the 10 to the 9. So you're doing, instead of doing like complexity 2 to the 20 times 10 to the 6, you would just do complexity this plus this. That passes in the time. I don't know if that was clear. Any questions?
Okay, thank you very much. Okay, good. Okay, so I would like to, unless there is a demand for another one of those, I'd like to move on to what we were, to try to finish up the previous class, okay, which was on pattern matching. And so what I would like to do, here's my plan now for the rest of the day. I'm going to talk about pattern matching until coffee break, and then regardless of where we go, pattern matching is history. But then we will afterwards talk about network flow things. And I'm going to talk about two different aspects of pattern. Last class, when we talked about pattern matching, it was about edit distance, when you're looking to match patterns in an inexact manner. There's also a world of exact pattern matching, which is very important, and among other things has there's a relevant data structure that's very powerful called a suffix tree or a suffix array. How many of you know about suffix trees? Okay, how many don't know about suffix trees? Okay, that sounds good. That's half and half, and that's good. And about suffix arrays? Probably about the same, okay, is what I'm guessing. Okay, but I think there's interesting stuff to talk about there. Okay, so I want to now talk about exact matching problems. And, one other question, just to double check. You guys, I've seen some people say they want to read my slides or something like that. I gather the slides have been being sent out over the Telegram or whatever you guys used. So if you want to see the slides, you can look there, and they're on the website, which is good. Okay, so when I think of string matching problems, there are three classes of string matching problems, and exact string matching problems. The first class is when you are given a text, one text, you're given one pattern, and you want to see is that pattern in the text, okay? This just means no, you're not going to do any pre-processing, okay? You just have a string and a text, and if the string is of length n, if the pattern is going to be in it, it better be less than length n, or else it's not going to be in there. But this is the kind of thing you use a linear time pattern matching algorithm like KMP or Boyer-Moore, or the one I'm going to talk about today is something called Rabin-Karp, which many of you may know. But it's an interesting issue. There is a second class of pattern matching problems where you have one text that you're going to be looking for queries in many, many times. The example here is, suppose you want to look whether something is in the Bible. Is the Bible changing? No, Bible is fixed, doesn't change, okay? But people may want to know, have different questions of what is in the Bible, okay? So if you want to answer those kind of questions, you want to take the Bible and build an index on it so it is fast to ask whether a question, something is in the Bible. Does everybody see that? Doesn't have to be the Bible. It can be Skinner's book, okay? It can be the human genome, any long string you might want to build an index for. And that's kind of the second class of string matching problem that is important. And for this, we will use suffix trees, talk about suffix trees and arrays. That's the classic way to handle that kind of problem. The third class of problems is where you have variable texts, but a fixed set of patterns. What's an example of this? Now, I don't know Portuguese, but in Portuguese, are there dirty words you're not supposed to say? Okay? Okay, do you guys know these words? Okay, I think some of you know these words, okay? Now, you could imagine building a program where you're taking, let's say, this, text of what's going to appear on the news, and you want to check, make sure nobody says a dirty word on the news, right? So here you have a world where you have do the number of different dirty words change? Probably not. I imagine your parents knew the same words that you know, okay? And, but the texts change. Every day there is new news going over this thing, right? So in the variable text fixed pattern world, you would like to do something to analyze your patterns, build a data structure on your patterns to make it easy to recognize the patterns on the text. Any questions about that? Those are, as far as I'm concerned, the three interesting exact string matching problems. Okay, do I have a clicker? I think I used to have a clicker, but maybe I do. Kaboom. Okay. So how does exact string matching work? Now there's many string matching algorithms that run in linear time, which I'm going to guess many of you know about. Now my favorite one, because it is very simple and actually gives some interesting ideas, is something called the Rabin-Karp algorithm, which is a randomized algorithm. How many people know about this algorithm? Okay, how many people don't know about this algorithm? Okay, fair enough, okay? What is the idea? The idea is to use hashing to speed up a, a computation. In particular, what does a hash function do? A hash function takes a string and computes a big number that represents that string, okay? And when you have this when two strings are the same, they produce the same number, okay? If you hash the word Steven Skeena, okay, with a particular hash code function, it will have one hash code. If you hash it again later, it will still have the same hash code. So what is the idea? If I want to tell whether two strings are the same, I can quickly compute the hash code of each string. If the strings' hash codes are the same, maybe they're the same, or likely they're the same. But if the hash codes are different, then they are definitely different strings. Does everybody kind of get that idea? Okay? So what is the idea of Rabin-Karp? The idea of Rabin-Karp is if I give you a string and I have a pattern, I compute the hash code of this part of the string, I compute the hash code of the pattern. Actually, I only have to do that once, right? I know the hash code of the pattern. If these two differ, the pattern can't be the same as the text, right? And now I can slide the pattern over by one and compute the hash code of the next window of text. And if that hash code matches the hash code of the original, maybe I've got a match, and I'm going to have to explicitly compare bop, 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 to test whether they're really the same. But if my hash code is big enough, it's very, very unlikely that I'm going to have an accidental collision. So I'm not going to waste a lot of time doing comparisons against explicit comparisons against the text, between the text and the pattern, unless it's going to be right. Right? I'm pretty if the hash codes match, I'm pretty darn sure they're the same string. Okay? Any questions about that idea? People get that idea, basically. Okay? Now, what's interesting is one other clever part of this, though. What is the running time of this algorithm that I am talking about? Okay, let me have a different picture here. What is the running time of that algorithm? Okay? If my pattern is of length k, how much time does it take to compute a hash code on a string of length k? It's linear in the size of the hash code, right? If it took order k time to compute the hash code of the first window, and if it took order k time to compute the hash code of every following window, what would this algorithm run in? What would be the running time of this algorithm? N times k. Okay? Because here, every time I compute the hash code, it seems like it should take the length of the pattern. Okay? Any questions? The magic of Rabin-Karp is that it does a very, very clever hash code, okay, so that you can compute it quickly as you slide over the text. Okay, let's go and look at this thing. What is the hash code for the string? The hash code here is, I am going to treat a string, if it's a binary string, let's just say it's a binary string. You guys are used to thinking about a binary string as a number. See, we got binary strings there, right? And you know that this in binary string is 1 plus 2 times plus 2. Not 4, not 8, plus 16, plus 32, plus not 64, plus 128. What is the hash code for Rabin-Karp? We're going to take each bit, okay, each letter of our string and multiply it by the base d to the I. Just like in binary, we're multiplying it by, binary is base 2, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the, you guys know this, right? So what is my code? I'm going to interpret it my hash code as a base D number for whatever D I want it to be, typically the alphabet size, okay? And I'm going to multiply it by the, let's say, the numerical value of the alphabet symbol. You know, again, I think in terms of ASCII code, you know that every character has a code associated with it. And I'm going to take this mod Q for some random, random prime-like Q, okay, to be, give me a number that's at most Q that represents the string. Any questions about that hash code? That should be familiar. What is clever? An interesting property of this hash code is that when you, which isn't property of most hash codes, is if you slide over the string over 1, you can incrementally adjust this hash code in time that is constant, regardless of the length of the pattern. What is the idea? The hash code of the slid over pattern is what? If this blue was the original pattern, when we slide it over, we've got to get rid of the first part of our pattern, which is this. We've got to add the last part of the pattern, which is this. And we multiply what's left of the hash code, or the hash code, by D to shift it over. Okay? And so when you do this, it's now only constant time to compute the new hash code. And as you slide over, bop, 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 okay, you will get that. Any questions about that? This is interesting to me because this is a linear time algorithm I can understand. Many of the other linear time string matching algorithms are very detail oriented. And I couldn't reproduce that with a gun to my head. This I could do with a gun to my head, right? Any questions about that? And this is an example of a randomized algorithm. And randomized algorithms are actually very important in real algorithms. Now, in programming contest stuff, you guys probably don't use randomized algorithms, or am I wrong? How many of you use randomized algorithms a lot? Okay, many of you do, okay? There's two different kinds of randomized algorithms. Ones that don't always produce the right answer, but usually do. Those feel like trouble on a programming contest, okay? But there's ones like this that the randomization is in the amount of time it will take, where you're hoping not to get unlucky. What does getting unlucky in this algorithm mean? If you're an unlucky person, what is going to happen? Is it going to give you the wrong answer, or is it going to take too much time? Take too much time. What is unlucky going to be? If you compute the hash code of the window and it happens to match the pattern, and when you match it, it goes, yeah, oops, okay? And you've wasted that time. And if you did that every single time, then you'd get in trouble. Yes?
In contests, we usually assume that we never get false positives. And so when it hash matches, we just take it as a match.
Okay, whether that's good hygiene, I don't know, okay, okay. Any questions? It's interesting that, okay. Any questions about that? Okay, so we know how to solve one of our three problems, okay, exact matching of strings, when you variable text, variable pattern. What about the case of the dirty words, okay, where you're given a bunch of patterns, okay, and you want to try to analyze them, okay, into what you call it, so that you can have a fast data structure to do it, okay? Here, the general answer is to use build what you would call an automata, okay, on the patterns. Okay, and again, this may be something everybody knows. But what is the idea here? The idea here is, suppose my pattern was the word nano. This is what you would call a finite state machine. It's a transition machine. It's a network, a graph, I guess you would call it, where from every node, it's a directed graph, where from every node in the graph, okay, you're going to add have links associated with with characters to tell you what other state you go to. Here, every vertex represents a state, and we're trying to represent the state the word nano, just one pattern. I don't know if there's a language where that's a dirty word or not, but let's just remember the word nano, okay? So what is interesting here? Okay, the possible states of recognizing nano are NA and nano, okay? As you can imagine that as a text comes by, you'd like to, depending upon what the output, what the next character is, what state do you go to, okay? And if it was a N, if we're here, on an A, you would advance to the NA state. If it was an N, you would stay in the N state. Otherwise, you go back to the so far I haven't recognized anything, right? A more interesting case here is like this one. Suppose I have an NAN so far recognized. If I have an O, then I've recognized the full pattern, okay? If not, I'm going to go to a different prefix depending upon what the answer here is. If I have an NAN, if I get an N, I would go back to the N state, because NN isn't part of it. If I got an A, I'd have, the last part of my text was NANA, I jump back to here. Okay? Any questions about this? Do people get the idea of this automata? The goal here is, for every state, you want to go through all the letters and go back to the longest prefix that goes back to where you were. And there's an algorithm for doing this, okay, building this automata. But of course, it could be built by brute force if you don't want to use a clever way of doing it. Okay? Any questions about that? Okay, so this is one that is useful to know about. But I think that the main attraction, maybe the most interesting of the pattern matching tools, is something called a suffix tree. And I'd like to go through this because if you use suffix trees right, there are a lot of very interesting algorithms you can, or problems you can solve quickly. So what is a tree? A trie. Okay, trees, binary trees, you know all about. A trie is a data structure on strings that is designed to speed up pattern matching. Okay? And basically, assuming we have a word, a dictionary, perhaps it's a dictionary of all dirty words in Portuguese, perhaps it is a dictionary of all, anything you want, a set of words. Okay? What a trie lets you do is recognize, okay, any pattern in time proportional to the length of the pattern. Okay? And let's just take a look at it. Here we've got a picture of a trie. What is the idea here? If you look at this trie, let's go back, bunk. Here we've got a trie. The dictionary consisted of what words in English? Okay? If we look at a path going down this thing, this first one was T-H-E-I-R. That's there. There's another word in English that's there. T-H-E-R-E. W-A-S-W-H-E-N. Does everybody see? There's also a word in English that's the most popular word called T-H-E. What is the idea behind the trie? If you have a dictionary of, in this case, 5 English words that I have, I'm going to build a tree-like structure, a rooted tree-like structure going down, where the fan out is proportional to the size of the alphabet. How big is the alphabet in any language? Constant, okay? In English, it's 26 letters. In Chinese, I don't know, but maybe it's, I guess thousands, okay? But it's constant, okay? Generally, for the languages we deal with, it's going to be a small constant, okay? What is the idea here? It's going to basically be a tree where at every edge is going to represent another character in the tree. The leaf represents every word in the tree. And in order to, if I have a text and I want to know, is this text a word in the tree? All I do is I start at the root node and say, what's the first character? If the first character was A, it's not in my dictionary. Okay? If it was a T, I move down to the next level. It should be clear that in time proportional to the length of the pattern, I can recognize whether or not a string is, the string that you're giving me to query with is one of the words in my dictionary. Okay? Any questions about that? You can tell people are bored looking, so there's not any questions. But why is this amazing? This is actually more amazing than you think. How big is the dictionary? Suppose the dictionary had n words. Okay? How long does it take, given a text, to tell whether your word is one of those n words? English has 1 billion words in it. Okay? What? It doesn't depend on the size of the dictionary. This is actually kind of an amazing thing. Okay? So that's, we should respect this. Okay? The time it takes to match is proportional to the length of the pattern. Once you have built this structure, okay, the structure will have, be of size n if there's n words in the dictionary. Maybe n times the longest pattern in the dictionary. Although, as you can see, that a lot gets shared. So long as they are shared part of the word, that will reduce the size of the trie. Any questions about that? Okay, so tries are a good thing. Okay, they're easy to build, and and they let you do pattern matching fast. Okay, good. Now there is a very special type of a trie called a suffix trie. Okay, it's so special a trie they tend to call it a suffix tree, but it really is a trie. Okay, what is the idea? The idea is it is a trie of all the suffixes of a string. The input is a string, let's say the Bible, okay? The Bible will have a certain number of letters in it. I don't know, it may have 1 million letters in it. I don't know the exact size of the Bible, right? But you can, every one of, what it is, the suffix trie is it's a trie of all the suffixes of that text. So if you have its text of length n, okay, how many different suffixes are there? of a length of a string of length n? N, okay? Basically, there's the whole string without a first character, without the first two characters, first three, first four, first dot, right? And by convention, we're going to add one extra character to the end of our string, which is a kind of end of string symbol, okay? So we're never going to play with the empty string, just for convenience, okay? So what is interesting about this? If we build a trie of all the suffixes of a string, how can you now tell what good is that? Okay? What if you want to find a particular pattern? Let's say you want to know whether Skina is in the Bible. Am I mentioned in the Bible? Not the editions that I'm aware of, but how would you prove that to someone? Okay? You'd like to know whether Skina is a substring of that text. The Bible's a long book, okay? How much time should it take to find whether this pattern is in the text? Okay? If we have built a suffix tree, what do we know? If Skina is a string in the Bible, then there exists some suffix where Skina is the prefix of it. Does everybody kind of see that? And when we get to that magic point in the book where Skina appears, there's going to be a suffix there. Because it's a trie, if I want to recognize whether the pattern Skina is there, I start at that thing. Is there one of the suffixes that begins with an S? Good. Is there a suffix that begins with a K? After that there's a note from the S suffix that begins with a K. Yes. I, E. If we got all the way down to A, I made the book. Okay? But in fact, you will find that I don't appear there. I'm not going to break the suspense now. Any questions about that? This is important to see. If you haven't seen it, this is actually now cool. If I build this trie of suffixes, I can search my string for any of the substrings in time proportional to the length of the substring. How many substrings are there in a string of length n? Not n, okay? N squared, okay? So all n squared patterns can be found in time proportional to their length using just this tree of length, this tree built on a string of length n. Any questions about that? And if it was easy to build a trie, I'm now telling you build a trie on all the suffixes of a string. In principle, it is easy to build a suffix tree. Not necessarily fast to build it, but it should be clear that it's easy to build one. How do you build a trie? Let's just think about this, just to make sure we understand it. How do I build a trie? Okay? I'm going to want to add each pattern in incrementally. This is the easiest way to do it, right? So what am I going to do? Up to a certain point, I've got myself a trie. It looks something like this. If I have a new pattern I want to add, what do? I basically will start trying to look up my pattern. If it's already there, then I don't have to insert it. But if it's not there, there's going to be a branch where it's suddenly going to be a no pointer was. That's where I will insert my new suffix, my new dictionary element for a general trie, or a new suffix for a suffix tree. Any questions about that? Okay, do people see that this part should be still easy? Okay, any questions about it? And if not, ask about it. Okay, good. Okay, how much space does this suffix tree take? as we've been talking about it now. Suppose I give you a tree of length, a string of length n, and I ask you to build the trie of all suffixes. How many leaves will this thing have? N. Why is it n? Well, because every pattern is going to be ultimately represented by a leaf. Okay? How do we know it's not going to be a leaf? It's going to be a leaf. Remember, looking back at my trie, were all my patterns here leaves? If you looked at this trie, no, right? Why is it that in a suffix tree, every pattern is going to be a distinct leaf? Does anyone remember? Because I added this weird end of string character, right? That's going to guarantee that it's going to diverge off, and so the general case is it's always going to be a leaf. So I've got a tree, it's got n leaves in it. Each suffix is represented by a leaf. How many characters? What's the height of this tree going to be? What? N, where n is the length of the string. Why is that? Because if you look back to my trie, what does my trie look like? I have a node for every, character on the path down, right? The longest suffix is going to be of length n. Okay, which suffix is that? That's the whole string, right? The suffix starting in the first position. How much total characters will this tree have? Just to make this thing respectful. We agree we've got a tree that now has a height n. It has n leaves in it, right? What is the worst case number of characters that can appear in this tree? Okay, about this. Let's think about it. If we think about it as, the usual way that you come up with a worst case bound is what? You take the number of things times the worst case, right? So if you think about that, the height of the total number of characters in this tree potentially could be n squared. Does everybody see that? Is n squared good or bad? Bad. Okay, n squared space. We didn't like n squared space yesterday, right? And in fact, it can get that bad, okay? What would be a kind of a string, just to think about it, which would really produce a bad suffix tree? What? If all characters were different, you're saying if this was in Chinese or something like that, where you have enough of an alphabet, that if every character was different, what would that look like? That would look like a tree that looked like this and everything goes down, right? That would be bad, okay? Can such a thing happen in a language like, let's say, a binary language? 0, 1s? Well, it can't happen that badly because my top node's going to be only a branching factor of 2. But can I still have a quadratic number of things? Yeah. What? Think about a random string. Okay? What's going to happen if I have a random string? Okay? Now, in order to have a trie that shares a lot, okay, what's going to happen? The moment I have a pattern that is unique, from then on it's a leaf and it goes all the way down, right? If I had a random string, okay, then what's going to happen? By the time you get to a length of about 2 log n, okay, it's very rare that a pattern would appear twice, okay? And then you're going to have something that's going to look like a complete binary tree for like height log n or 2 log n, and then it's going to go down, okay? So what do we know about these suffix trees now? Okay, I think it should be clear now to everybody. You know how to build them if you had to. Okay, again, if the gun was to your head, could you implement a suffix tree easily? I'm sure you guys could implement a trie. I'm sure you could insert all suffixes. The bad thing is it's going to potentially run out of memory because it's quadratic in size. Okay? Any questions about that? Now, it doesn't have to be quadratic in size. Okay? This is the next kind of amazing thing. I claim that it doesn't have to be quadratic in size. Okay? In fact, you can make this tree linear in the space that it uses. How do I make a suffix tree in linear space? Well, look at the thing over on the right over here. What do we know about our suffix tree? First of all, how many leaves are there in the suffix tree again? How many? N. If we have a tree with n leaves, how many interesting internal nodes does the tree have? Okay, what is an interesting internal node? A node that has one child is not interesting. A node that causes a branching of two or perhaps more is interesting. What's the maximum number of interesting nodes you can have in a tree with n leaves? N minus 1. Okay, or yes, yeah, n minus 1, I think the exact amount. It might be less than that, depending upon if the branching factor is bigger. But if it was a binary tree, if he was using a binary alphabet, you'd have n leaves and n internal nodes. So is there a way we can take our suffix tree and compress it so we don't have these nodes that are just these one character? This is the thing that's killing me, is that I've got a long path of nodes here, okay? That's why it was quadratic space, right? How can I get rid of that? Okay? Okay? I claim one thing that's neat in a suffix tree, what do we know about the contents of everything in this suffix tree? Okay, text-wise. We know that it has to be a substring of the original string we were building it on. Right? Does everybody kind of see that? So what if I represent my suffix tree as follows? I'm going to keep one copy of my original string. I don't know why I'm writing this, but here there's my original string from 1 to n. And now, whenever I have a path up, let's say here was a path, right? There was a branching over here, and then this went on till the end, right? How can I represent this string? Well, this started in a particular position of the text, right? This particular substring, if it goes to the end, was from some position k all the way to the end. Okay? If I store one copy of the string and I keep track of at each node the start and stopping point of every of the string that I'm representing, in two numbers, I can represent the string associated with a particular, in this case, it's really associated with an edge. Okay? So for every edge, I'm going to have a I'm going to represent the string not by explicitly writing the string on the edge, but by writing the starting point and ending point in the original string. Okay? And now, if you see that, now you should believe I can store a suffix tree in space that is linear in the size of the string. What is my space? N to store the original string. The topology of my tree is going to be n leaves, n minus 1 internal nodes. That's order n. And on every one of the n edges in this tree, okay, I am going to store two numbers, okay, the starting point and ending point of the string. And when I now want to walk down this string, how do I do it to recognize a pattern? I'm going to start at the beginning and say, okay, if I go over on this edge, this is from 1 to, this suffix starts at 1. String sub 1 is an X, is the character an X. Once I start going down that path, okay, I will keep following along the string until I hit, by the time, if this substring was represented by from 1 to 3, I will use that as instruction to match the first 3 characters, and then I'm at another node, and I can follow it down. Do people understand how I'm encoding this tree? This is important because at this point, this is still something I think people can do without being, knowing some magic to build a suffix tree. What is the idea? I'm going to build my trie interactively, incrementally, one string after another, one suffix after another, okay? And I am going to represent each node by a pattern, by a substring, subrange in the original text until it diverges, okay? And if I do this, I can represent my suffix tree in linear space, and I can still search in time proportional to the length of the pattern, okay? And all of this is good. Any questions about that? This I hope people understand. Yes?
I kind of lost your explanation when you're trying to do the try for suffix. Can you explain it again in another one?
Okay, which part are you uncertain about? Say this one more time.
Uncertain about how can we identify the substrate so we can build the suffix?
Okay, so how can you identify the substring? Okay, let's think what your decision is at a particular node. I think you want to know how to build it, or you want to know how to use it to search? Use it, okay? So what is the situation at the root? Build it, okay? Okay. Well, think okay, so in my suffix trees, I'm going to build it incrementally. If I have a string, in this case my string was XYZ, XYZ, there are going to be a total of 7 substrings, suffixes I'm going to insert. This is going to be a trie. So in order to insert another string in the trie, I basically am going to start from the root and walk down. Okay? Let's say from the existing suffix tree. Suppose I have a new string, which we'll call XY skeina. Suppose based on the board, the trie that I have on the screen, I want to now insert XY skeina. Maybe we'll make it, let's make it XYZ, XY skeina. How would we go and insert this thing? Well, in this trie, where would it be? It should be on this branch. I would look at the 3 characters from here. XYZ. I would now walk down from here, XY, and now there's supposed to be an S. This edge of the suffix tree, from here to here, right up between the 1 and the internal node, is where this new pattern should go. So what am I going to do? I am going to replace this edge in the suffix tree by what? It used to be an edge XYZ, XYZ. What am I now going to do? I'm going to replace this by a subtree, and then here was a 1. What am I now going to do? I'm going to replace this by adding turn this edge into an XY. And I'm now going to say here, if it was a Z, it would go to a 1. And otherwise, this edge is going to be a skeena. Does that make sense? Or not? Now you're saying yes. Okay, so I'll give up now. Okay? Any questions here? Okay? Now, the good thing about this is that, the good thing about it is this is simple I can do. Okay? The bad thing is, what is the running time of this? The running time of this is still might be n squared. Okay? Is it usually going to be n squared? Let's think what happens on a random string, though. What's going to happen on a random string? Okay? Well, a random string, we said, would produce a tree where, after log n levels, okay, everything branches off into a long suffix, right? Is a long suffix expensive for me to deal with now? No, because it just know the character position to n, okay? So this isn't as bad as it looks anymore, right? If you give me a random string, this is going to be n log n, okay? So there are fancy linear time algorithms to build this thing, but it's no longer such a terrible, thing to build. The space is linear, and on a random string, it's going to be n log n. Can anyone give me a string that would be terrible for this algorithm, though, where I'm repeatedly inserting suffixes? What would be an example of a very expensive string?
Repeated.
What?
Repeated everything.
If I had a string that was of the form A, B, this would be a bad string to implement. Why? Because I'm always going to have to go walk down to the end of the... what's that suffix tree going to look like? It's going to look like a shared pattern of A's where off of each one of these is a B. Okay? And so I'm going to have to walk down to the end. So incremental insertion, usually random-wise, should be n squared, should be n log n. It's not that complicated. If you're unlucky, okay, it could be n squared. He was telling me he didn't worry about luck before, that he used these randomized algorithms and didn't bother to test. So if you feel you're not going to worry about luck, this is good enough. If you don't feel like luck, there are these fancier algorithms that are kind of amazing that will build the entire tree in linear time. Okay? But this is a piece of magic that you can read about. I'm not going to go, the details are intricate. But it's kind of an amazing thing. Okay? Any questions about the suffix trees, how they are structured, how you build them? I think from what I've explained, you should be able to say, yes, I can build a suffix tree, and yes, and it can take linear space, and yes, I can believe I can search down it, and for any substring, I will find it in time proportional to the length of it. Any questions about that part? That much you should all believe.
Sorry.
Yes?
Can it be built faster than O n squared?
It can be built. There exist algorithms that will build this in linear time. I'm not going to teach you them, okay? But the truth is, there is, if you're interested, this is an interesting thing to look at. They're intricate. They involve maintaining pointers to places so you don't have to walk all the way down when you do the insertion. Okay?
So it is short enough to get it in the competitive programming notebook? But it's like a repository.
Okay, this is something I would personally rather not implement in a short period of time, but you guys have probably faster hands than me. Okay, so maybe you can do it. Or maybe you can bet on the fact that if they give you a random string, the other one isn't going to be so bad. But let me show you more interesting. What I'd like to show you is amazing things you can do once you know how to build suffix trees. Let's say you can build suffix trees in linear time. This is an amazing thing, but it can be done. Now let's show you what you can do with a suffix tree that is algorithmically interesting. What if I give you two strings, okay? And I want to know what is the longest substring they have in common. I give you the word livestock. I give you the word sea liver. LIVE is in common to both of those words, right? That's the longest substring that's in common to both words. Suppose I give you two strings and I ask you what is the longest substring in common to both of them. How would you go about doing that? Okay, how would you have done it before we talked about that? Before we talked about suffix trees, how would you do that? Maybe by doing something like edit distance, that would be n squared. Okay. What is the way to do this with suffix trees? What if I build a suffix tree on the first string, weird character, the second string? Now I've got one suffix tree. I've got one string that consists of word 1, strange character, word 2. Okay? What do I now know? Okay? If I build a suffix tree like this, what is going to be the situation? With every suffix tree, it consists of a top part with shared patterns. Remember, if we have a suffix tree like this, how many times did this pattern occur in the text? Okay? You remember as you walk down a suffix tree, each edge represented a part of a string, right? What do we know about how often this pattern, if this was A, B, A, B, A, how often, many times did A, B, A, B, B, A, B, A, B, A, how many times do we know that it occurred in the text? The number of leaves below it. This has to have occurred at least twice, right? And if this is what it looked like, if that's what the tree is, it occurred 3 times. Okay? What do we want to know if we want to know when is liver, sea liver, going to be, which is the longest word in common to both strings? Well, we have a tree. How many nodes does this tree have? It is n, where n is the length of the two concatenated things. Every one of the suffixes of this string, which remember consisted of word 1, word 2, $. Okay? Every one of these things is going to be a suffix. What do we want if we want the longest string in common to this and this? What is it that we want? If we want to know what is the longest string in common to this, okay? It is going to be the deepest node in the suffix tree, which has at least one descendant from this part and one descendant from that part. Okay? Think about this for a second. So what are we going to do? Every one of these leaves was a suffix. Some of these are going to be word 1 suffixes, meaning they start with word 1. Some of them are going to be suffixes that start with word 2. What is the longest common string to both of these? It is going to be the deepest node in terms of the number of characters, the length of the substrings on the path, such that there are children of type 1 and type 2. Do people see that? Okay? Do people see that that's the right characterization or any question about that? Okay? How do you find this thing? Well, you guys have heard of depth first search, right? You've got a tree. You can go depth first search, bop, 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 bop. For every node on the way down, you can figure out, does it contain, as you come back up on a depth first search, for every node, you can say this is a 1-2 node. This is a 1-2 node. This is a 1-2 node. This is a 2 node because it didn't have one, right? Once you now know for every node whether it has descendants of type 1, type 2, or both, you can now go and count how many on the depth first search, how many characters have you accumulated to get down here. The deepest node has both labels is going to define the longest common string. How many people see that? So I'm hearing some weak hands, okay? But maybe now the hands are stronger, okay? Any questions about that? This is kind of amazing, yes?
When you reach a leaf, do you have to store additional information in that leaf to know whether it's a first word or a second word?
Okay, do I need to explicitly store for every leaf whether it's a type 1 leaf or a type 2 leaf? I could. Or I could really just store what you typically store for each one of the leaves is the starting position in the string. If the starting position was less than this, it's a type 1 leaf. And if the starting position is greater than that, it's a type 2 leaf. So if you do that, you don't need to store the label. Any other examples here? Questions here? Okay. This is, yes?
If I reach a node that has both type 1 and type 2 leaves,
Yes.
that means the node contains S1 and S2.
That means if I have a node here that has both type 1 and type 2 leaves, what does that mean? The string on the path down to that node has to appear in the first word and also in the second word. How do I know that this pattern didn't occur from here and span the two of them? That would be kind of a danger, right? But how do I know that that isn't going to be the case? Well, because I put that weird character here, okay? There's no word that, that weird characters will be enough to tell me that I'm not going to get the pattern from here. If it contains the weird character, it won't be in type 1 or type 2. Okay? Any questions about that? Okay? So this is where I think suffix trees get really amazing, is that you can use them to solve problems on strings that are, seemingly otherwise hard to find. Okay? I'll do one more because I know we've got a coffee break and we've got network flow and all this kind of stuff. Suppose I give you a string and I want to know what the longest palindrome in it is. What is a palindrome? A palindrome is a word that when you read it backwards says the same thing. Does everybody know about palindromes? My favorite palindrome is is a man, a plan, a canal, Panama, right? You guys are from closer to this part of the world, right? If you go back there, how do you tell if a string is a palindrome? If I say madam, how do I know that this is a palindrome? It's matching this. It's not hard to tell whether a string is a palindrome, right? But how do I find the longest string that is a palindrome? How do we know that Madam I'm Adam is the longest palindrome within this string? Well, it's pretty easy because it's in blue, right? Okay? But more to the point, algorithmically, how can I find the longest palindrome in a string using a suffix tree? Okay? Any ideas?
It's longest common between a string and its reverse?
Okay, you're sort of saying, what if I take my string S? What if I put maybe I put my pound or something like that in there just to keep it separate, and I take the reverse of the string? It's almost right, but it's wrong. But let's think about why it's almost right. That's the more interesting thing. Okay? Why is this almost right? If you have a palindrome in a string, what do we know? It appears in the string, and it also appears in the reverse. Is that correct? So what do you want to know? He thinks what you want to know is, what is the longest string that appears in a substring, longest, let's say, substring, that appears in S and appears in the reverse of S? That I showed you how to do, right? I just showed you that's how to solve this problem. Okay? Why doesn't it do what we want? Does everybody see that it almost does what we want? Because certainly if there's a palindrome, it appears in S and it appears in S reversed. Okay? Any questions? Why isn't it exactly finding the palindrome?
A string could just have a substring and it reverses somewhere.
Right. What if I told you that I give you the word Skeena, and I say cat, and I say A-N-E-I-S-K. Right? I think I have to make it S-K. K-S. Okay? Now, this string and its reverse appear, but they don't appear in the right place. Okay? Is there a way to fix this problem? Okay? It turns out there is a way to fix this problem. Okay? If you add least common ancestor queries to the tree. How many people know about least common ancestors in trees? Okay, there's fancy data structures, more magic for doing this thing. But what do we know if there is a palindrome? Let's put it this way. If we do have madam in the string, madam in the string, what do we know? If this is going to be a palindrome if, starting from this position in the string, it matches in the reverse starting from this position in the string. In his concatenated string, what are the positions of this? This is from the ith character here to the what? N plus n minus ith position, I believe. Right? So the ith character here is going to be the n minus character here. It's n characters to step. What you really now want to know, if you know the leaf that starts on position I, and you know the leaf starting at position n plus n minus I, those are two leaves of the tree. What is the length of the common substring of these? We find the lowest common ancestor node and walk back there. So for every node in this tree, we can know how deep it is. With your LCA magic, how long does it take to find the lowest common ancestor of two nodes in a tree? Constant, if we're using some magic, right? If so, what does that mean? You're doing n LCA queries. N times constant is n. You built this tree using the suffix tree magic. How much time did that take? N. Okay? In linear time, you can now find the longest palindrome. Okay? And the basic things, this is where I'm going to have to stop because I do want to get you to coffee break and I do want to have something about network flows. But this is where suffix trees become interesting, is that they let you solve a lot of string algorithm problems. that you couldn't otherwise solve. Okay? Any questions? Yes?
So, are you claiming that if you have one leaf to check if there's a palindrome starting there, you only have to check one other leaf?
Right, because what am I going to want to say? Let's think about it. What is the longest palindrome? If we look at madam here, if you start from the D, the interesting question, if it's, let's say your palindrome is of odd length, there is a central character, and then you want to know what's the longest match between the suffix from here and the suffix in the reverse starting from here. So you only really need to look at, from every position, one pair for the longest odd length palindrome, and if it was an even length palindrome, you would want to start from the reverse from here and the forward from there. So you're doing two of those things from every position, each of which took constant time. Any questions? Okay, in that case, suffix trees, I didn't get the suffix arrays. If I run out of stuff or we have a gap later in the week, I'll talk about that. They are beautiful things. But there's coffee. I'm getting an angry coffee symbol. Go to have coffee, and we will resume here and talk about network flows. Thank you. if I build a suffix tree of this, it's going to be a tree where one of the leaves is going to be position number 4. Okay, so let's okay, I could do it by taking the whole part. But actually, if I don't, I can't do it because I don't know how far do I need it. To know, if I start from here, I don't know where the next part is going to be. Suppose I start in the center, okay? I think that's the rules here. Okay, so two things just I wanted to say before we get into the material again. One is, it seemed clear that there were people who were interested in the suffix trees and how they work and stuff like that. If you want to do more reading on suffix trees and the amazing things about them, the book I remember I like best is a book by a guy named Gusfield, Dan Gusfield. He has a book called Algorithms on Strings. There's some biology in the title, but don't get scared with that. But it's basically a string algorithm book. And this will tell you about, suffix trees and about a lot of the good algorithms on strings. So that's one announcement. Second announcement is I heard from my Tanzir. He says he's put another hard problem on the test for today, so hopefully we'll be able to keep you guys busy. Any questions about that? We'll find out when we have it. Okay, what I'd like to talk about today, today's programming contest is supposed to be about things related to matchings and flows. And so I did want to go through this. How many people here think they know are good with network flow algorithms? How many people are not good with network flow algorithms? Okay, more people. Okay, so this is good. Network flows is a hard area, is one of the harder areas of graph algorithms. And so this is why I wanted to talk to you guys about this. And so my lecture for today is going to be on a little bit of the theory behind network flows, why network flow problems are interesting. I'll then talk about one of the main uses of network flows, which is on finding matchings in graphs, okay, bipartite matchings particularly. I'll then talk about a couple of applications. I then expect to run out of time, but if I don't run out of time, I have a little section of advice on things that I may give. Okay, any questions so far about what we're trying to do here? So what is the network flow problem? The network flow problem is a world where we have in general, a source node S and a sink node T. We have an edge-weighted graph. Okay, so the weights are on the edges. And the weights kind of represent the capacity of each pipe. I like to think of that each edge represents a pipe. Okay, the amount of water that can flow through it in a unit time is the capacity of the pipe. Okay, what are you trying to solve a problem? If you physically built this graph out of pipes, okay, where every node had a capacity, and if it was a low capacity pipe, you would have a small hole. If it was a high capacity pipe, you would have a big hole. You stick a hose at node S, turn on the water, and you see how fast is stuff coming out of T. That is the maximum flow problem, okay? And the maximum flow problem is basically trying to predict how much stuff will come out the end, okay, if we put as much water as we can through the network T at S. In this particular graph, what is the maximum amount of flow we can have if every pipe has equal capacity? Let's say every pipe can put 1 liter. I guess you got right. Here we're in a world where you guys have 1 liter per second, okay, through the thing. Okay, if all the pipes have equal capacity, my claim is that putting the pipe through in picking these edges, okay, will maximize the amount of flow, right? Does everybody see that here we've got, how do we know that if all the pipes have equal amounts of flow, that this is the optimal amount of flow? It looks like I can get 3 units of flow through this network. How do we know we can't get 4 units of flow through this network? Okay? There's some pipes we're not using. Does everybody see that? Why do we know we can't put more flow than 3 units through this particular network?
Because there are only 3 pipes that come from the source and only 3 pipes that go to the sink.
It's constrained ultimately, although there's plenty of pipes if you cut through the network here, there's in fact only 3 pipes from the source and 3 pipes from the sink. All of those are saturated as much as possible. So we can't hope to get 3, but we can get 3, we can get 3 units of flow through this network. Does everybody see that? Is there more ways to get 3 units from this network? Suppose, let's say you guys are from the southern hemisphere. You like flows that go from the southern part of the network. Okay? Is there another way to get 3 units through this network that won't use the pipes up so high? Okay? It should be clear what. What else could I do? I could conceivably take my blue one and have it go bunk, bunk, right? And then have my red one go bunk, 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 okay? So there can be, the same maximum flow can be realized many ways, okay? Any questions about that? Okay, so this is good. Now, when we talk about network flows, there is another problem here that you should also talk about, which is linear programming. How many people here are familiar with not dynamic programming, but linear programming? Okay, about half of you, okay? What is the idea of linear programming? In linear programming, we are given a bunch of constraints, okay, which we'll typically can think of as being a plane, that's a line that's going to cut the space of possible solutions into 2 parts, things that are feasible or feasible. So typically, we're going to be given a bunch of constraints where, for example, this orange constraint, there's a direction. We're only interested in solutions where it represents, a point below that line, the yellow line. And it only represents a point that is above the red line, and above the blue line, and above the grayish line. Notice the grayish line does not cut off more solutions than the bluish line. In linear programming, we are given a bunch of these constraints that essentially chop the space of possible solutions into legal parts and illegal parts. And in linear programming, we're given a bunch of constraints, and we're given an objective function, and we want to know what's the highest scoring legal point. In this case, the northernmost point, okay, is going to be what we want. We want the northernmost legal point, the one that is on the right side of all of those constraints, and that in this case is the black point. Okay? Any questions about linear programming as a concept? It's a geometric problem, but where you're given a bunch of planes, you find what is the intersection of all those planes, and then once you have it, if I give you a criteria of which point in that intersection is best, find me that optimal point. Okay, that's linear programming. Any questions about that? Now, there is a easy way to express a network flow problem as a linear programming problem. Okay? And this is why I want to bring this out, and a lot of the theory about network flows is because there's this theory about linear programs. Suppose I have a network flow. if I have a network like this, here was my network, what is a property of a legal flow? Remember, water is coming in from, oh, actually, I guess in Brazil, you guys have a lot of oil here, right? Is that right? Or some oil? Am I right? Not as much as you'd like, maybe. It's coming in from this side, okay? And there's a source, and it's going out that side, which is the sink. At any intermediate node, what do we know? The flow into the intermediate node has to equal the flow that is coming out of it, right? So if you look at my linear program thing, I've got an equation here and a constraint like this that says that the sum of the flows going into node K, okay, actually this is the sum of the flows going into node J is equal to the sum of the flows going out of node J, okay? And that's got to be true for every node except the source and the sink, okay? It may be that there's a limit to how much stuff you can pump in the source, okay? Again, we were just saying Brazil doesn't have as much oil as it wants, okay? If you have a big network with very, very thick pipes, you may not have enough oil to fill it, okay? You know, your oil wells produce it at a certain rate, okay? Maybe there's a bound B, okay? Such that you can only have at most B units coming in or B units coming out the sink, okay? And there is a constraint that the amount of flow at every edge has to be less than the capacity of the pipe, okay? Or you might have a more general version. Maybe someone is going to stick a gun to your head and say you have to have at least this much flow go through this pipe, okay? What's clear is you can express these constraints about how much flow goes through an edge by linear constraints. Does everybody kind of get that idea? And that there are these linear equations you can write, or inequalities, that govern what you want to have, what are the constraints given by a flow network. And once you see that, then with linear programming, you can specify an objective function, okay? Give me the maximum value of something that satisfies all those constraints. In the flow problem, if you want to maximize the amount of flow going through that network, what is the constraint, the optimization criteria you want? You want to maximize the flow that is going through to the sink. Okay, that's the sum of the flow on all the edges to the sink node. If you want to solve another more general problem on flow, suppose for every edge, okay, on the pipe, you not only have a capacity, but you have a guy that's charging you for how much you're using the pipe. To ship, let's say that I have a pipe here, and to ship a unit of flow through this pipe, they're going to charge me C reals. Is that how you pronounce it here? Okay? So what is the idea? You could also imagine a world where if there is a price per unit flow on a particular pipe, the cost of the solution is going to be basically the cost per unit flow times the flow on every edge, summing that up. And the minimum cost flow problem, okay, asks what's the cheapest way to get a certain amount of flow through a network, okay? Both of these can be expressed as linear programs. Any questions about that? People get this idea. Now, in the programming contest world, do any of you guys do linear programming? Okay? The answer may be no, the answer may be yes. Do any of you guys do linear programming? Okay?
Not often, but.
What?
Not often, but.
Not often, okay? So there are algorithms. In fact, when we get to computational geometry, I may show you how to do linear programming. I don't promise it because this hasn't been made up yet. But you know, certainly finding the intersection of a bunch of half-planes in 2 dimensions, that seems like a perfectly reasonable programming contest kind of thing to do, okay? And if I then give you a particular objective function, finding which is the point in that intersection region that is the one that scores the highest, okay, is a perfectly reasonable thing to make you do. Especially because I guess in linear programming, one thing you know is that the optimal point is always a vertex of this thing, okay? So in 2 dimensions, everything would be great, but when it comes to network flow, 2 dimensions would be incredibly boring, okay? So, but in general, you would, you know, this proves to you that you can use linear programming to solve network flow problems, okay? And sometimes it's very, very useful to think of network flow problems through linear programming. Any questions about that? Okay. Thank you. Okay. So why is maximum flow, and I'll say minimum, the flow problems, why are flow problems important? Okay? There are a couple of reasons, philosophically and practically. One is that, first of all, occasionally someone gives you a network and really wants to find out how much stuff flows through it. So, you know, if you're the oil industry, you care about network flow. But if you are, in general, one of the main importance to people like you is that there are a lot of famous graph problems that turn out to be solvable using network flow techniques. Okay? I'm going to assume you guys have seen done an infinite number of programming problems on networks. You guys minimum spanning tree in your sleep. You find shortest paths in your sleep. Okay? Network flow is kind of the branching point to a to a more advanced set of graph problems, okay? That is one reason why. And the 2 examples that I'm going to show that are very important are bipartite matching and connectivity testing. What's the smallest, you know, how robust is a graph, okay? So those are practical reasons to care about network flow. The other, let's say, one of the theoretical reasons why you care about network flow is that it is one of the most powerful linear programming problems that you can solve without using linear programming. Okay, that's, I guess, the way to think about it. We talked here about linear programming. You guys are very hot to trot programming algorithms people. You don't want to implement linear programming too much because linear programming is an algorithmic problem that to do well is very complicated, okay? In higher dimensions and numerically stable and all that. So it's about the most linear programming-ish problem that you can solve using the kind of combinatorial algorithms that we like. That's one reason why it's kind of important philosophically. Any questions about that? Okay, good. There is one other important thing about, actually it's funny. Let me close my eyes for 1 second. It's funny, I lost a snide comment here. Sorry, maybe I'll make it with, even though I lost it. First of all, actually, you guys, how many of you are familiar, in your university, I'm going to guess, how many of you are computer science-ish students? I'm going to imagine almost all of you are computer science students. Are there people who study operations research? OR. Okay, so you people here are saying, yeah, I know my linear programming, right? Okay, there's kind of linear programming, operations research. They're very algorithms and operations research are very similar are somehow similar fields in that we care about about optimization, finding the best thing. Okay, the OR people care about finding the best thing. But you guys tend to use as your tools things like linear programming and something even stronger called integer programming. Okay? So there's different ways of thinking about it if you're an OR person or a algorithms type person, to a first approximation. What is one thing that's that's true about linear programming? Linear programming, remember, you had a bunch of inequalities, and you had to try to find the point that satisfied all those inequalities, okay, and also scored the best by one criteria. That was linear programming. Now, it's possible to find very, very simple linear programs where you have integer coordinates, okay, integer coefficients, but the optimal answer isn't an integer. Okay, let's look at this. Suppose I give you the equation x equals y. That's a constraint. Okay, and I give you the constraint that x equals y plus, x plus y equals 1. Okay, this is actually not only a constraint, this is completely solved, actually. The region that's intersecting this is just a point. But I now ask you then to find what is the maximum value of y. What is the maximum value of y subject to these two constraints? A half. Does everybody see that? You're saying, wait, coefficient here is 1, 1, 1, 1. This thing is 1. Even though you have integers defining the coefficients here, the optimal solution here was y equals 1/2. Okay? This is fine, it's true. Okay? Now, in a lot of things, when we're dealing with discrete things, we want our solutions to be integers. Okay? You are used to, if you're counting how many things are, they're supposed to be integers. Okay? Now, the version of linear programming where you force the solution, it has to be an integer. Okay? In this case, what would be the solution that is optimal, that is an integer? There is none, you give up, okay? But in general, you can make linear programming harder by insisting that the solution be an integer, okay? The amazing thing about the network flow integer program is that it always gets solved to being integers, okay? Excuse me. Give me a second here. The amazing thing about the network flow problem is that if you give me a network and all the weights on it, all the limits on the capacities are integers, the optimal network flow, when you solve it by linear programming or just the optimal linear solution already, is always going to be an integer. Okay? And this is kind of an amazing thing when you stop and think about it. Okay? Because again, general linear programs can have fractional solutions. Okay? That's life. Okay? But the matrix that comes from the network flow problem is always going to be is always going to give you integer solutions. This matrix has some property that it is totally unimodular. What does totally unimodular mean? Ask the people who are OR people. I bet you they know, okay? Because they studied this kind of thing. But from your point of view, what's interesting? network flows are always going to have integer solutions if the weights have integer capacities. And this is kind of amazing in some ways. Suppose we have a network where the flow limit of an edge is 1. How much flow is going to go through that edge, okay, in an optimal solution? 0 or 1, okay? That means that we've kind of got the equivalent of almost a Boolean variable here, okay? Boolean variables are logic-like things. They're no longer numerical things about stuff flowing through pipes, okay? So this is the thing, this integrality property is kind of the amazing thing about linear programming, about network flow, is that you can count on, if you have linear weights, it's going to be if you have integral weights, it's going to have an integral solution. Any questions? Okay, good. So how do you find the optimal network flow through a graph? Okay? And the algorithms that you guys, kind of people, are going to implement, okay, are based on an idea called an augmenting path. What is an augmenting path? It means you go through the network and you try to find a path from the source of the sink where the pipes still have more capacity, and you incrementally push flow through the network so that it has more that it takes advantage of this capacity. And the interesting property that makes solving network flows possible by a combinatorial algorithm, the kind of algorithms we like, okay, is the fact that we can basically do this kind of an augmenting path approach. It's in some sense a greedy algorithm, okay, or in some sense an incremental algorithm. If there is a way to push more flow through the network, okay, find a path where you can push more flow through the network and keep doing this until there is no path where you can send more flow through. Once you have that, you've got reached the global optima, that we've reached a local optima. And the interesting thing is it turns out to be a global optima. And that's what gets us into this notion of an augmenting path. Any questions about that? This I suspect many of you have heard. Let's just see if we can see an example. I mean, again, let's look back at our example here. Okay, suppose we're operating on the left, okay? What does that mean? If every one of these edges had, weight 1, what would be the way that we would do it? Originally, so long as we find some path from source to sink, where all of there is 1 unit of flow that's available to be used on these edges, then that would give us 1 unit of flow. We keep repeating it so long as we can find a path where we can send more flow through, okay? That will, until we can't run out of that, then we hit hit an optimum. Any questions so far? Okay, let me keep back here. So what is the algorithm here? The basic idea here, it's a little bit more complicated than what I said, because you might send flow through a network and then regret the choice on some level. It might be that you might need to change, okay, some of the flow that you sent through it. So what is the idea here? We take as originally our sort of residual flow graph. We start with the original, okay, graph. When we find a path from S to T, okay, let's say we use the path up top, Okay? If we have a path from S to T and we use this top one, how much path can we put through this thing? There's 5 units constraint here, 7 units constraint there, 5 units constraint there. We can put at most 5 units of flow through here, okay, with that one path. Once we've done that, we can now change our graph to reflect what the, how much flow we can put through it after that path is there. Certainly, we can still put 2 more units of flow through this edge 7. Because it had capacity 7, we put 5 units through it. Okay? But we also have the opportunity to reroute these 5 units of flow. There's 5 units going this direction. Okay? If we now go in this graph, maybe there is a path which will use the back edge here and send more going the other direction. Okay? So the residual flow path network consists of, whenever we send a unit of flow through a network, we break that edge into a directed graph, a directed edge. The weights of it are how much of flow capacity remains, how much capacity was used in the other direction. Any flow from here to there that is a positive thing, we can now send through and send more flow through it. Okay, so there's this process of finding augmenting paths in this residual graph that will, we keep doing finding augmenting paths until we, until it has converged. We can't send any more. Any questions about that? Okay. Fair enough. So, implementing these, this algorithm that looks for augmenting paths is not really that hard, okay? Again, you know how to find a path in a graph. You know how to find the shortest path in a graph. That was going to be Dijkstra's algorithm. If you were looking to find the shortest path in a graph that was unweighted, that was breadth first search. Okay? What is the basic idea or implementation that you use for network flow? Again, we build this residual graph. Okay, what do we know for every edge? There is a capacity, there is a flow in one direction, and there's the residual capacity that remains. That would be the capacity minus the flow. Looking for an augmenting path. My network flow algorithm looks something like this. Basically, find an augmenting path from source to sink. If the amount of flow I can put through that is greater than 0, then basically implement that path, change my network, add that amount of flow through it. Then search for another augmenting path, perhaps by doing a breadth first search, and calculate what is the smallest edge on that path, so that's going to be the limit to how much flow I can keep doing this. This is the basic structure of a network flow algorithm, okay, with details of keeping that up. Any questions? Okay, I think looking at the code is probably very boring, but I'm going to make you do it anyway. Okay? What is the volume of a path? The volume, how much can I get through a particular augmenting path once I have got it? It's the capacity of the smallest edge on the path. So if I know how to do a path, I look for the smallest weight edge on that path. Then when I update the graph, after I have put this flow through it, I reduce the capacity in the forward direction, I increase it in the backwards direction, okay? And that's basically the algorithm. Any questions? Okay. Now, let's think about what happens when we do augmenting paths. Okay? An augmenting path, remember, you had a source for S, you had a sink T. Okay? An augmenting path was basically a path through the graph, okay, such that if you found the minimum weight edge, you could throw that much flow through it. Okay? You have a choice of many different paths. Now, we have shown that if the weights on the graph are integers, the flow through every one of these paths is going to be an integer. That's good. We like integers. But one is an integer, and one is a small integer. Okay? It might be that one of these augmenting paths might affect only a small might increase the flow only a little. Okay? And so we may need a large number of augmenting paths, okay, in order to get from one place to another. Okay? Any questions about that? How many augmenting paths, if we have a graph of n nodes, how many augmenting paths might there be or distinct, independent augmenting paths might there be from S to T? Certainly a couple ways of looking at it. What's a way to build a graph on n nodes where there's a lot of paths between S and T? What kind of a gadget might that be? Maybe something where you have a bunch of diamonds like this. This is the way I like to think about it, right? And if you have a graph like this, you could always either go up or down. That would mean that there's like an exponential number of paths, right? If we insist on the paths not overlapping each other, think about a network where, let's say we have, these things all have a capacity of n. We go to n over 2 vertices, and all of these are compared by edges of weight 1. Now here we've got n squared edges, okay? And each augmenting path is going to be from here through a different edge over to the sink, right? So everybody see that if I have a complete bipartite graph here, how many augmenting paths are there we would have to do to pick all the flow from here to here? Each augmenting path is going to include only one of those order n squared edges, right? So it should be clear that if you go through this, you might need to do, in certain graphs, have to do n squared augmentations, regardless of what algorithm you use. In fact, it was proven that if you do the Edmonds-Karp algorithm, if you do something where you always look for the shortest path in terms of the number of links, okay, you will always be able to reach a global state after n cubed augmentations. So the problem is, regardless of this, whether you have a graph where you've got an exponential number of paths, or a graph where you need to have at least n squared augmentations, if you always use BFS to select the shortest augmenting path, you will be able to find the maximum flow in a polynomial number of augmentations. This network flow algorithm runs in polynomial time. Any questions there? Okay, this seems boring, I can tell, okay? But what's good? We know how to compute that. What's even cuter about this is that if you remember, there were two flow problems. There was the maximum total flow, where we were looking to do the largest augmenting path thing, okay? And there was the minimum cost flow, where we wanted to find a way to send as much flow as we can from here to here as cheaply as possible if there was a cost for using each edge. Well, using Dijkstra's algorithm, we can find the cheapest cost path to send flow from S to T. And if you want to find the minimum cost flow, you use the same basic augmenting path structure thing, but find the shortest path in a weighted sense, in a cost-weighted sense, rather than the number of links. If so, that will find the cheapest flow. Any questions? Yes?
Would opposite edges in the residual network have negative costs?
No, they presumably still have the same cost, okay? But there's a limit to how much more you can send through it, right? Because the cost is applied at the end in some sense, okay? Any questions?
I didn't understand that idea. Can you explain a little bit?
Okay, so let me try to do this. I want to get to the applications of this, but I want to make sure, I guess we should make sure that the algorithm is clear. What is a situation in a capacity sense? Every one of these edges has a flow capacity, how much water you can put in it, and it also has a cost. This costs 1 real per unit flow. This one costs 2 reales per unit flow. Now we have a network where for every edge we have a capacity and a cost. If we want to find the cheapest way to send flow through this, we're going to want to find which augmenting path is the cheapest way to send flow. And that is going to be the shortest path in the cost, with the cost weights. So if you want to find what's the cheapest way to send 1 unit of flow, where every edge has a cost associated with it for sending 1 unit of flow, the cost is going to be the cost per unit flow on every edge that you use. That means the shortest weighted path from S to T. Okay, and that's the kind of thing you would find from Dijkstra's algorithm. So it should be clear that you can find the cheapest path for sending a unit of flow through the network using Dijkstra's algorithm. Once you have the cheapest path way to send flow from here to here, send as much of it as you can on that price. The amount that you're going to be able to send along that path is the lowest capacity of every edge on that path. You send as much fluid as you can at the cheapest price, and then look for how much can I send, what is the next cheapest price that I can send more fluid through. And so it's the same kind of incremental inserting, augmenting path procedure. But we're going to consider the paths in order of how cheap they are. Okay, and if we do that, we find the cheapest way to send the flow. Does that answer your question or not?
I was thinking that the packages are to maximize the flow, but the way you're saying it is like to minimize the cost. Like if you find the minimum cost augmenting path,
Yes.
you will have the best flow and cost flow solution at the end. And
Right.
it's not really clear to me how the packages, like how does a package redirecting flow with another cost work in this algorithm?
When you use the back edges, okay, you flip that edge around again, okay, It's not just a question of the remaining capacity being used. You might alternately decide to say, I would like to send, to redirect some of the flow that I had there through this other direction. Okay?
But then that would generate a negative cost, and that takes the extra.
No, the cost is the amount of flow that you're putting through it. It doesn't matter which way the water is flowing, you're still paying the cost through the pipe. Yes?
When you use a residual edge,
Yeah.
you have to unpay the cost.
Okay.
So it's as if it had negative cost.
Okay. Okay, fair enough. What I'd like to talk about, though, once we have the algorithm down, the algorithm is something you can look up. It's Edmund Karp's algorithm. You can do this. What is interesting is the properties of what you can do once you know how to compute minimum flow. Once you know how to compute the maximum flow. Okay? One thing you can do is find the minimum cut through a network. Okay? That is because of the fact that the maximum flow through a network is the same as the minimum cost weighted cut through the network. Notice that if I am looking at every augmenting path, there is a constraint. There is an edge that is kind of the smallest edge on any that's constraining the flow along that augmenting path. If I blow up each of these edges, okay, I won't be able to send any more nodes flow from S to T. So there's a connection between the maximum flow through a network and the minimum cost through and the minimum cut through a network. Okay? And so if you see this connection, you can compute the size of the minimum cut, okay, by using network flow. And this is a useful thing to be able to do. Any questions about that? This is a kind of famous thing to cut. Now, what other applications? Well, what time do we end here? Unfortunately, at 11:30? Yeah. Okay, so we're a little behind here, but I'm gonna let you go. But what else is important that you can do with network flow? One problem you can do with network flow is bipartite matching. This is a very important algorithm problem. What is the story? If you are given a bipartite graph, a matching is a subset of edges such that no vertex appears more than once. Okay? A perfect matching is one where you find a subset of edges where every vertex is on exactly one edges. If we think about traditional marriage, where men and women married each other, okay? If you had a set of men and you had a set of women, okay? If you had what men were willing to marry what women, okay? A question of whether or not every person could be coupled off is that of finding a bipartite marriage, a bipartite matching, okay? Any questions about that? How do you find bipartite matchings? Using network flows. This is interesting, okay? Suppose we have a network where every edge has weight 1. Suppose we have a source connecting to all the vertices on one side and a sink connecting to every vertex on the other side. What is the maximum matching? If I can get n units of flow through this network, if every edge has a limit of 1, what is the situation? Every vertex in the middle, I can only get 1 unit of flow to this vertex. Because of integrality, the only way I can get that 1 unit of flow out to that vertex is going to be by, by sending it along one edge. And so finding the small, the largest set of edges, matching edges I can do in the bipartite graph is just finding the network flow. Do people see this? This I think people should see. Okay? So if you know how to do a network flow, you know how to do bipartite matching. Now, in general graphs, the problem is harder, but with the time we have, let's not worry about it. Anyway, let's not worry about that either, because we have limited time here. What can we do with network flows and matchings? There are a bunch of interesting applications, and this I find that I think a lot better about bipartite matching than I do think about network flow. So learn to think about matchings, not just flows. But one problem is, given a network, what is the smallest number of edges you can delete to disconnect the network? Okay? We said there was this max cut thing. That would, max flow equals min cut, right? So if I have a vertex S and a vertex T, I can find what is the smallest number of edges to cut through, okay? By finding the maximum flow from S to T, I can find that's going to be the minimum cut from S to T. If I want to find what's the smallest number of edges in the entire graph, what is the number of, how do I do that? I have to try separating S from every other node in the graph. It should be clear that if I run n-1 max flows, I can figure out which is the play to send from S to someplace else that I can send the smallest amount of flow. That is going to be the minimum cut. Okay? Any questions? So that's useful. There is also the question about vertex connectivity. Okay? How many vertices do I have? Okay, boom. Okay, I don't know what that's happening here. I think I know, I did something dumb. Okay, in this graph, what's the number of vertices I can delete to disconnect the graph? Not edges. I can delete 2. Okay, why is that? I can delete this one and this one. Vertex connectivity is how many vertices do I delete from S to T. And the claim is that you can also do this in with network flow. Okay? Basically, it turns out that the minimum edge cut set, as we said, was equal to the number of, well, disjoint paths, let's not worry about, for vertex connectivity. Okay? We want to try to find the number of vertex disjoint paths that we can find between S and T. This can also be found by network flow. If you adjust, if you change the graph a little bit. Suppose I want to make it so that the edge flow through a graph is going to represent the number of vertex deletions. Suppose I have a vertex in this original graph where there are, it has a certain number of, it depends whether it's directed or undirected. If I represent vertex V by a gadget V in, V out, okay? This edge, if I give this an edge capacity of 1, this edge can only be used once in one flow. Okay, does everybody see it? Because we had integrality. Okay? If I replace every vertex in the original graph by one of these gadgets that has split it with an edge between it, I can ensure you're only going to have flow go through this vertex exactly once. And with that transformation, the edge cut in that graph is now a vertex cut in the original graph. And so I can find out how many vertices to delete. Okay? And I'm regretting that this is very fast and I know you can't follow it. But does everybody see that you can also, in principle, compute vertex connectivity with that? Okay? Let me show you one other application, because I know I'm supposed to end in 3 minutes. There's a couple of other applications in the slides. But let me show you one final application of matching and flows that I find interesting and very powerful. Okay? You guys know about Eulerian cycles, I believe. What is an Eulerian cycle in a graph? It is a walk through a graph where you visit every edge exactly once. Okay, is there anybody who hasn't seen that before? That I think everybody knows, okay? Now suppose each of these were streets, okay? And that at least in the United States, you were a guy called a mailman who drives around in a truck and stops at every house and drops off mail. Okay? Suppose the city had a road network that looked like this. What's great about an Eulerian cycle in that graph? Okay? He will visit every edge in the course of driving back and come back home. And as he goes over every edge, he will drop off their mail, right? Is this the shortest possible way the mailman can drive and drop off everybody's mail? Yes. The answer should be yes. What's the problem? Are all cities Eulerian? Okay? Is the roadmap of Campinas an Eulerian graph? Probably not. How do you find the shortest possible, okay, tour to, the shortest possible tour for a mailman to drive in a city so that he or she visits every single edge in the graph? If it was Eulerian, we were done, right? When is a graph Eulerian? You guys know this, I think, right? When is a graph Eulerian? If it's an undirected graph, when is it Eulerian? When every vertex has even degree, right? And it's connected, right? If we consider a city that looks like this, does anybody get their mail? No, nobody. Some people aren't going to get their mail, right? But if it's connected, but even degree, it's Eulerian. What if it's directed? When is a directed graph Eulerian? Does anyone know that? What's the critical property you need? You need to be able to get into it as many times as you can get out of it. Okay, the in degree has to equal the out degree. What happens if the mailman lives in a city where this is not true? How do they plot the best route to deliver the mail? Okay, well, we need to find a way to augment the graph so that it is Eulerian. What does that mean? Okay, if I have an odd degree vertex, I want to add an edge to that graph so it's not an odd degree vertex anymore. How do I do that? I need to connect it to another odd degree vertex, right? So what do I want to do for this case? What if I built a graph where I had every odd degree vertex and I add a weight between any two odd degree vertices, which is the amount of driving you would have to do between these two vertices, right? Look at this graph. It's no longer Eulerian, right? But here I've got an odd degree vertex, and here I've got an odd degree vertex. What would the cost be to connect them, to make them even degree? I could do it by 2 going through this way, right from bunk bunk. I could make it 2, 5. This would be a terrible way to do it, right? By finding the shortest path between here, I can find the cost of adding an edge or making the trip again if I'm the postman to make it Eulerian. What is the cheapest way to make it Eulerian? What do I want to do? I find the cost between every pair of odd vertices, and then what do I want to do? I want to add a set of edges that will make them all even. What's the cheapest set of edges that will make them all even? I claim it's going to be, if I have these are the odd vertices graphs, I want to find what is the lowest weight matching that I can add to this graph between the odd degree vertices. And once I have that, then the graph is Eulerian, and I can find the cheapest cycle. Okay? So this is how they call this the Chinese postman problem. But what is the important idea? If it was Eulerian, I know the cheapest store. What's the cheapest way to make it Eulerian? It should be clear that if I build a graph connecting the odd degree vertices with the cost of what they're doing, the lowest weight by matching in this graph are the smallest pair, cheapest paths to add to the graph to make it Eulerian. How many people semi-see that? How many people see it enough that I can end it now and let you go do your thing? Okay. Yes, question.
Why is that graph bipartite?
Why is this graph bipartite? The answer is it isn't bipartite. Okay? But how do I make it bipartite? What if I now say I have inversions and outversions of each vertex? Okay? And I now want to know, I want to go from an invertex to one of these. Okay? If it was a directed graph, okay? Do you see that I'm adding directed paths here? Now I can figure the cost of going from here to here. I want to add it so from every vertex, I have a way to go. Let's just think about it. In the directed graph, there's some vertices that have a higher in degree. Some vertices have a higher odd degree. Okay? By treating it as a directed graph between the ones I want to go into and the ones I want to go out to, this becomes then a bipartite graph. Okay? And so either for the undirected graph version, either I find a way to make that graph so that I can use a similar trick to make that bipartite, or I could use the general graph matching, which is also polynomial, although that's hard. Okay? Any questions about that? Yes?
The weight of the edges is the shortest path.
The weight of the edges is the shortest path between them in the original graph.
And is it always possible to transform a graph to have an invariant cycle? Is it always possible to do this?
It's always possible by adding, the moment I make the degrees all even, then then the graph is Eulerian, and there has to be an Eulerian cycle for it, right? And if it's an odd vertex and an odd vertex, if I add an edge between them, what happens? They're suddenly both even, right? How many, can I have an odd number of odd vertices in a graph? No. That would be odd, right? So no. So I pair up the odd vertices. Now it's even degree. Now I can do that. Okay? Any questions? Yes?
It needs to be a perfect matching.
So then here, what I want is I need a perfect matching, because I need to pair up the maximum possible matching would be one which is a perfect matching. Okay? So then I want the minimum weight, highest degree matching, and that's how I will do this. Okay, any questions? Okay, I'm sorry I ran late, okay, and good luck today, and I'll see you guys, good luck on the contest, and I'll see you guys tomorrow as well. Okay, thanks a lot. Yes.